So now we're getting into chapter 5 of Calc, and we're just talking about logarithms to start off. So honestly, it just starts off with a little review. Just remembering the properties of logarithms, or if you don't remember them, knowing them for the first time. So this is the first one. If you have things divided inside of a logarithm, it changes to subtraction. So if you were trying to make a nice list of all the log properties, which probably would be decent to have in your notes, if we have the ln of a divided by b, something divided by something, that's going to be the ln of a minus the ln of b. Simple enough. I just dropped my pencil. So this is another really important property. So one property they're actually skipping over there. I don't know why they didn't put it. I guess because it comes directly out of that one. You could derive it from that one. But similarly, if you have something that's multiplied, if you have the ln of a times b, ln of something times something, that's going to change to addition. So that's going to be the ln of a plus the ln of b. So the second thing they're doing here is probably one of the most important properties of logarithms. So first off, they remind you that if you have a square root, that's to the 1/2 power. So I'm sure you remember that from the power rule derivatives. So we do that, and then if you have a power inside of a logarithm, you get to bring that out to the front as the coefficient. So if you want to write down that property, that's going to be that the ln of a to the b equals b times the ln of a. And I'm going to go and throw in a little secret property. I call this the secret property of logarithms. And it states that if you have log of something raised to a power, or base something raised to a power, where the base itself is raised to a power, that's the big secret property. And then if this is, say, raised to also some power, like we know we can bring out the power on the top and multiply it, but the power on the bottom, you can bring that out to the front and divide it. So that's going to equal y divided by x times log base a of b. So that's a useful property sometimes. Sometimes it makes problems that were supposed to be hard a lot easier. Okay. What are we doing here? Well, this is the same thing as before. Oh, this is the property. So this is more of a problem. So this is showing that if we have the ln of 6x over 5, I mean, they split it up into different steps. I would say here you should think about everything on top is multiplication, and everything on bottom is division. So when you're going to separate it, everything on top is going to end up being positive. So the positive ln of 6 plus the ln of x, but then the stuff on the bottom is negative. So minus the ln of 5. And that is exactly what they have. See how they just did it in separate steps. They showed that you have 6x divided by 5, so you did 6x minus 5, and then they used our property number 2 up here, where if things are being multiplied inside, you can pull them apart and make an addition. And then D is definitely just a problem. Let's write that down here and do it ourselves. So the ln of x squared plus 3 squared over x times the cube root of x squared plus 1. So there's just a lot going on here. But I think like with a lot of things in math, it's not any harder. It's just a lot. So like what we said with the last one, everything on top, we're going to make positive. Everything on bottom, we're going to make negative. So we're going to have the ln of x squared plus 3 squared. That's the positive one. And then minus, we'll go ahead and separate this because see how we have the x and the cube root of x on the bottom? So we'll do minus the ln of x, but then also minus the ln of the cube root of x squared plus 1. Okay, so now we can do it more, right? Because here, I guess we don't need these parentheses. See how that thing is squared. So we can pull that squared out to the front whoops, whoops, whoops. We can pull that squared out to the front. And then this, just like the square root is 1/2, we know that a cube root is to the 1/3. So we can pull that out to the front. So what do we end up with? 2 times the ln of x squared plus 3 minus the ln of x minus 1/3 the ln of x squared plus 1. And there we go. And important to remember that when it's addition outside of the logarithms, you can put it together. But inside the logarithms, it would have to be multiplication. So at this point, there's nothing more we can do because we have x squared plus 3. If it was x squared times 3, we could pull it together more. But with x squared plus 3, it's just stuck. And if we could factor, like maybe if that last one was x squared minus 1, we could make that x plus 1 times x minus 1 and then separate it more. But here, we don't want to go into imaginary numbers with it. So we'll just leave it at that. And you see, that's more than they did. Or I probably cut off the rest, to be honest. And we just finished it out ourselves. So there we go. That's just reminding us of properties of logarithms. So here we're just trying to remember like exactly kind of how to estimate logarithms. So ln of 2. We try to think, what is ln of 2? Well, one way I'd kind of just like to write it out. So I'm a big fan of just equations. I think if you can write it as an equation, then you can solve it, right? So we're thinking e to what power equals 2? Sorry, I thought my internet went out for a second. So anyway, e to what power equals 2? Well, remember what e is. E is like kind of close to 2, right? It's just a little bigger than 2. 2.7. So if we want to raise it to some power to be 2, it's going to have to be like 0.9, right? I call it like 0.9. I don't know why it looks like times 9. I don't know. I'm iffy on that. I don't think I've ever estimated that. I don't know what a ln of 2 is. But I would say it's definitely less than 1. That's why I'm not... I mean, I know that. Well, what's this if it was e to the 1/2? If it was the square root of e, I don't know what the square root of e is. But to get 2... Oh, I would call that like 1.5, wouldn't I? But no, this definitely has to be less than 1. This definitely has to be less than 1. So let's call it 0.9. I'll be happy with 0.9. The ln of 2, e to the what power gets you 2? Yeah, probably about 0.9. And then now with our ln of 32, I'm actually going to use our answer above. Maybe we can see if this makes sense. So the ln of 32 is the ln of 2 to the 5th, right? Which means we can bring this out. So this is 5 times the ln of 2. So if we're calling the ln of 2 0.9, we're calling this 4.5. And then let's think for ourselves, does that make sense? E to the 4.5. Is that going to be about 32? Well, what would 3 to the 4.5? 3 to the 4.5 would actually be huge. And E is closer to that. E is closer to 3 than it is to 2. So I'm not super happy with this 0.9 anymore. Maybe 0.8. And call this 4. What's e to the 4th? E to the 4th is a lot more likely to be 32, I think. But still, if it was 2, but it's not. It's more like 2.5. Let's call it 2.5. So what's 5? Wait, what was I even trying to think about? So we're calling e 5 divided by 2. And then we're trying to think about what's 5 divided by 2 to the 4th power. Oh, then I'm doing like 625 divided by 16. That's too much. That's too much. I mean, estimating is not even that important anyway, right? We're just saying this is definitely somewhere between 0 and 1. And this is somewhere between 0 and 1 times 5. I mean, does 4 make sense? I do think 4 makes sense. I shouldn't have the 0.0. That's just based on the A answer. And then what is this? E to the what equals 0.1? Well, that's just like... negative, isn't it? Am I actually doing a really bad job? Should these be negative? Well, no, the ln of 2 is not negative. I just don't know why I think the ln of 2 was like 1 point something. It can't be. It has to be 0.8. But why did I think the ln of 0.1 had to be negative? To get less than 1? Yeah, because e to the 0 would be 1. So to get less than 1, it's definitely going to have to be negative. So here I'm thinking e to the what equals 0.1. I don't know. I think like squared, like a little more than negative, like negative 2.1. Because I'm thinking of like if e was 3 and it was 2, then it'd be like 1 over 9, which is like the 1 over 10 that we're looking for. So I'm thinking I'm going to go negative 2.1, and I'm feeling pretty good about that, to be honest. And those are just estimations. I think those are tough estimations to make with logarithms. I guess it's just thinking about e. Maybe I'm just not comfortable enough with e. I'm definitely not as comfortable with e as I am with pi. I would more ask to do estimations like log base 2 of 7 or something like that. Or maybe even better, just something like log base 2 of 15. And I would just ask you to think like, well, it's almost log base 2 of 16. So it's like almost 4. So it's probably like 3.9. And then I'd say we'd go to numworks and we would do the ln of 15. This is another log property, the change of base formula. It's just useful for calculators. You can do a specific base log in the numworks. It's just, I don't remember how to get to it. Wow, yeah. And then we'd be super right on with 3.9 as an answer. 3.906. Versus here, a moment of truth. How do we do? I'm ready to be embarrassed. 2.7. Ooh. I was comfortable saying that e to the 4th was 32. E to the 4th is 54. Ooh, that's tough. That's tough. All right, how about this? I was really happy with this negative 2.1. ln of 0.1. Negative 2.3. I'll take that. I'll take that. I'll take that. Yeah, we have calculators now. We have calculators now. So here's where the more fun starts. The derivative of ln. So I'm not even sure. Well, no. I was about to say that wrong. I know what the derivative of ln is, and I'll tell you. So the derivative of the ln of x is 1 over x. What I'm more curious about is how can we derive that? All right, so I figured out how to do it. And when I say that, I mean I looked up how to do it. But it's not that bad. So we're going to start, as we, I think, always should, with the limit definition. So we're going to have the limit as h approaches 0 of f of x plus h minus f of x over h. That's just your limit definition of a derivative, right? I think if we're proving a derivative, we should always start there. And in this case, we're trying to take the derivative of the ln of x. So let's do the substitution. So the limit as h approaches 0 of the ln of x plus h minus the ln of x over h. Okay. So now what? So next, we just got to use the property of logarithms. I came up with these next steps. I needed some help to finish it out. But remember, one of the properties, if we're subtracting logarithms, we can divide. So this is the ln of x plus h over x. And then over h. Okay. So now the step gets a little weird. But I'm comfortable with it, if you are. And you should be. I'm going to try to make you comfortable with it. So we're going to use a new variable, a little substitution. We're going to call it t. And we're going to say that t is equal to h over x. And then real quick, we're going to say, therefore, that means, if we multiply both sides by x, that h is equal to x times t. And then now we're going to stop doing this problem in terms of h, and we're only going to do this problem in terms of t. So, well, h is still going to be in there a little, right? But we're also going to say This is the key step that kind of was confusing to me. That because when h goes to 0, t goes to 0, right? Or more, to be more specific, what they said is that when h goes to 0, h over x also goes to 0. That's clear, right? When h is 0, h divided by x is 0, because 0 divided by anything is 0. And so that means that t goes to 0. So that's what's going to allow us to, instead of doing the limit with h, we're going to do the limit with t. But still as t goes to 0, because as t goes to 0 and h going to 0 is the same thing. Because that's how we set it up. And then now we can do the substitution. So what are we really doing now? Is we're actually not ready for it, are we? We have to do one little more little heart separation here. So we're going to separate this fraction inside of the logarithm to x over x, or 1, plus h over x. And then all of that will be over h. And so now you can see what I was going at with the substitution. So we're going to have the ln of 1 plus t over x times t. Okay. Makes sense, right? Uncomfortable with that. So then we're going to do a little wacky stuff. So we're just going to use the property of logarithms. The limit as t approaches 0. And this is 1 over, maybe I should write that first. This is 1 over x times t times all of this, right? I think that is something people forget a lot, but very important to remember. And that means that if we wanted to, and we do, we can rewrite that as a power. So we have the ln of 1 plus t to the 1 over xt. And then, even weirder, honestly, we're going to keep going backwards. We're going to keep like unsimplifying just because it's going to help us. So we're going to rewrite this as ln of 1 plus t to the 1 over t to the 1 over x. And that's the same, right? You don't usually go backwards, but you know if you have an exponent raised to an exponent, you multiply the exponents. But the beauty of this is now we could bring this to the front. I suppose, honestly, we could have left it at the front the entire time, couldn't we have? Let's actually do that. Scratch it. And this is why you shouldn't copy other people's work. You should do it for yourself, because you'll find better ways. Notice that this is 1 over x times 1 over t. So all we should really be doing here is then moving this 1 over t up into the exponent. And this, they did note this, that since that has nothing to do with t, that's just a constant in this terms. So we can pull that out to the front. And now we have 1 over x times the limit as t approaches 0 of the ln of 1 plus t to the 1 over t. And now that you see that, well, first off, you should be happy. As we already said, that's the derivative of ln. And what's going on with everything else? Well, when you plug in 0, you kind of have to know this. What is the limit as t approaches 0 of 1 plus t to the 1 over t? Well, that's e, not approximately e. That's equal to e. So what we have right here is 1 over x times the ln of e. And what's the ln of e? It's 1. It's 1 over x times 1. It's 1 over x. And that is how you derive the derivative of the ln, the natural logarithm. And so now here we can use it. So this is just a little chain rule, right? No worries. So we're going to do the ln of 2x, so 1 over 2x, times the derivative of the inside, which is just 2. And that's quite interesting, right? Because the 2's cancel. And you just end up with 1 over x. which is a little surprising at first, right? The derivative of ln of 2x is the same as the ln of x. But then you look at it again. If you use one of our property of logarithms, we have two things multiplied there, right? So that's the ln of 2 plus the ln of x. And what's the ln of 2? The ln of 2 is just a constant. And what's the derivative of a constant? It's 0. So we can see how whatever number that is there is just going to go away. And the derivative of it is still just going to be ln of x. That's pretty cool. So going on, I don't think we'll have such beautiful things happening. So the derivative of ln of this. So remember chain rule. So it's always 1 over that. And if you want to be quick about it, like I just did, let's not write the 1, because then we're going to be multiplying by the derivative of the inside, which is 2x plus 1. And then you should simplify if you can, but obviously you can't. So you're good there. All right, and this is product rule, right? Notice how I cut off the answers here. So we still got to be careful with our product rule. I was going to say we should do x to the x, but no. Taking the derivative of x to the x, if that was asked of me, I would rewrite it as this and take the derivative of this. So this is what we want to do. So it's product rule. So we got the derivative of the first thing, derivative of x, which is just 1, times the times the ln of x, 1 times ln of x, plus the normal function x times the derivative of ln of x, times 1 over x. So that's the ln of x plus 1. All right. And what about this one? So the derivative of ln of x cubed. So this is always weird, right? Do pay attention to how they wrote it. They didn't write ln of x cubed, because I think then we could pull this out to the front. But as is, I don't think that's allowed. I think we're going to have to be using power rule here. So we'll bring the 3 out to the front. And then that's still going to be squared, because decrease the power by 1, power rule. And then divide by, or actually multiply by, but multiply by the derivative of the inside, which is 1 over x. So that's what I was writing, is that we're going to be dividing this by x. It's a weird problem. I don't like that one so much. But yeah, that's the derivative of ln. So we'll probably get into the derivative of the log, and I'll probably have to pause again, but we're not doing that yet. So let's just do another one. I don't know why this is separate. This is just the same thing. What's the derivative of this? So we're going to do 1 over the square root, I guess because it's a 3-layer deep chain rule. So it's ln, so it's 1 over whatever's inside the logarithm, so 1 over square root of x plus 1. But then we got to multiply by the square root, the derivative of the square root. So what's the derivative of a square root? I had that memorized. It's 1 over 2 root, whatever's inside the square root. In this case, x plus 1. That's interesting. And then you got to multiply by the derivative of the inside, which is just 1 in this case. So why is that interesting? I hope you see it. We have the square root of x plus 1 times the square root of x plus 1. That's just x plus 1. So it's 1 over 2 times x plus 1 is the derivative of that. That's always kind of interesting to me. That you're starting with a derivative, and when you differentiate it, you get rid of or you're starting with a log, and when you differentiate it, you get rid of a log. I think that's very interesting. So I maybe see what they're going for here. It comes more into play on the next one, but let's use this problem as an early example. So one other technique we could do, there's nothing wrong with what we did, it just might have been a little tedious. So another thing we could have done is we could have used some properties of exponents. So ln of x plus 1 to the 1/2 is what we have, right? Because that's the square root. And then we can bring that 1/2 out to the front. So our function really here is 1/2 times the ln of x plus 1. And so now, if we wanted to take the derivative of that, that's actually super simple, because the 1/2 just sits there, and it's being multiplied by the derivative of the ln of x plus 1, which is just simply 1 over x plus 1. So that's a technique that you can use a lot with logarithms. So that is what we're going to do down here. So, like I said before, everything on top is positive, everything on bottom is negative. So it's going to be the ln of x, then positive. And remember, this is one of those things. We're not taking the derivative yet. We're simply rewriting it. So I'm going to go ahead and pull the 2 out to the front in this step. I think skipping steps is just good for your enjoyment. It just makes it more enjoyable, which is really what you want at the end of the day. Because when you enjoy it, you're ready to learn more. 2x cubed minus 1, boom. So the deal with this is just way easier to take the derivative than this. I mean, look at this. Here you'd have to use product rule and quotient rule and chain rule multiple times. All of that inside of an ln. I mean, that'd be crazy. You could do it, but this is going to be so much easier. Because now, see that, to remind ourselves, that's just f of x. Now we're going to take the derivative. Now that we've written it in an easier form to take the derivative of. Because now it's just the derivative of ln of x is 1 over x. This might be the most challenging one. So 2 over x squared plus 1. Right, it was 1 over whatever's inside. But then multiply by the derivative of the top. Or the derivative of whatever was inside. So 2x. And notice how easy it was. I didn't mean it was hard when I said it was the hardest. It just might actually be the hardest. Maybe this one is, because it's minus. Minus is already harder. And then 1 over 2x cubed minus 1. So, of course, that 2 joins that on the bottom. And then we're going to multiply by the derivative of the top. So we just have a 1 on the top so far. So we're going to be multiplying by a 6x on the top. 6x squared. Decrease the power by 1. Yeah, there we go. And we'll just go ahead and simplify. I'm not going to rewrite it all. We'll just make that the 4x that it is. And then cancel this. Go ahead and get rid of these parentheses then. And put that 3 there. And that should be it. And so just know that that's just a lot easier than having to use all those rules like you would here. You might get a slightly different form, but this is a great form. You can combine it to one fraction if you want, but that wouldn't be super useful. So this is pointing out that sometimes you can force it, even when it's not so obvious. That's what I forgot. So here, you could do the same. You could do, it's not even that bad, honestly. Quotient rule. I wouldn't really think to use ln. I would use quotient rule, power rule. You just know all that stuff. It's fine. But another thing we can do is we can take the ln of both sides, which is kind of crazy. So I'll just rewrite all of it for now. X minus 2 squared over root x squared plus 1. Right? I mean, we did it to both sides. So that's a legal move. You learned that in algebra and pre-algebra. If you do it to both sides, it's legal. But now we can take the derivative of both sides. So the only thing we just have to remember is we have to use implicit differentiation, right? Because over here we're going to get 1 over y times the slope times the derivative. I'll just write m. And then over here, and actually we're not even ready to take the derivative yet, are we? So let's move this down, because this is the whole point. Now the same technique we did last time we can use here. So we'll rewrite this as 2 times the ln of x minus 2 minus square root, so 1/2 ln of x squared plus 1. Now we'll take the derivative of it. And now see how simple it is. It's 2 over x minus 2 minus 1 over 2 x squared plus 1. And that was much simpler to do. The only thing you now have to remember is you have to like go backwards. We don't have to un-ln. Don't try to do that. We have to multiply both sides by y at this point. And of course, distribute. And is that wild? I mean, kinda. I don't know how far they want us to go with this. Because now if we multiply both sides by y, should I try to distribute it too? I mean, so y is x minus 2 squared over root x squared plus 1. So if I distribute that to the first one, I'm going to have 2x minus 2 on top, and then the root x squared plus 1 on the bottom. And then I'm going to distribute it to the next one, which really doesn't simplify nicely at all. We're just going to have x minus 2 squared over root x squared plus 1 times x squared plus 1 with that bonus 2 on the bottom. I mean, I guess then if we wanted to, we could combine it into one fraction. 2 times x minus 2 times x squared plus 1 for the common denominator minus x minus 2 squared over 2 root x squared plus 1 times x squared plus 1. I mean, that's disgusting. Is that the same thing that would happen if you just took the derivative with quotient rule and stuff? I kind of want to do it now. Let's change colors so it's obvious. So let's use quotient rule. So you do the derivative of the top, which is 2 times x minus 2 times the normal bottom minus the derivative of the bottom, which is 1 over 2 root x squared plus 1 times 2x times x minus 2 squared, all of that over x squared plus 1. So honestly, it does kind of seem like it's the same. So I'm going to be multiplying the top and bottom by root x squared plus 1. And so I distribute, that'll be just 2 times x minus 2 times x squared plus 1. And then when I do it to the second one, it'll just cancel out. So it'll be minus 2x, x minus 2 squared. Oh, but over 2, so that canceled out. And then all of that, I'm multiplying this times the bottom too. Root x squared plus 1 times x squared plus 1. So it's slightly different, isn't it? Where's the 2 on the bottom supposed to come from? Because this 2 cancels out, right? That 2 definitely should cancel. So I'm just seeing the 2 there. Okay, well, I see something I did wrong here. If there's a 2 here, then I need to multiply that by 2, and this would have to be 4. Also, there's no x. Okay, I must have really screwed this up. Dang. Dang, dang, dang. Okay. I mean, I don't know which one I trust more. Well, I already saw I made mistakes in this bottom one. It would just need the 2. It ended up becoming 4. But here the 2 cancels. I trust this more. Let me look it over. So the derivative of the top, 2 times x minus 2, times the bottom, square root of x squared plus 1, minus the derivative of the bottom, which is 1 over 2 root x squared plus 1, times the derivative of the inside, so times 2x, which is why the 2's cancel, and then times just x minus 2 squared. So there definitely should still be an x there. And I missed that here. I missed that here because I didn't multiply by the derivative of the inside. Big oof, big oof. So the 2's do cancel. Oh. So the 2's do cancel and the x is there. So I'm right here that then that would have to be that, but then that cancels, that cancels, that cancels, that leaves it at 2. So, yeah, I think that's a prime example of why just do it normally. You don't have to do logarithmic differentiation. Unless it's like really nutty. This isn't nutty enough to try to do logarithmic differentiation. Just do it normally. Quotient rule is not that bad. You can do it. I promise. Alright. The derivative of the ln of the absolute value of cosine of x. So I think we just like the absolute value is one of those things in calculus. It's just like so obnoxious because most of the time it doesn't matter, and I think this is just one of those cases where it doesn't matter. But do we have to maintain it at the end? Well, we'll think about it. So we're just gonna try to do chain rule right away. I don't think we have to worry about the cosine of x. The only reason, or the absolute value, the only reason we have the absolute value is because cosine is negative sometimes, and you can't have the ln of a negative. So they just do that to make you like be able to do it. So it just makes the graph look like this instead, which is fine. The derivative's not continuous, which we'll see. We'll see. Let's go. So what's the derivative of this? So it's 1 over the inside, which is cosine of x, and then multiplied by the derivative of cosine x, which is negative sine of x. So what does that leave us with? And that leaves us with negative sine of x over cosine of x. Which, what's that? Sine of x over cosine of x. I hope you're already screaming at the camera. That's tangent of x. So this is negative tangent of x. And we just don't have to worry about absolute value. Why not? Because this should be positive and negative sometimes, right? Like we know what the graph is look like. Sometimes the slope is positive, sometimes the slope is negative. So that makes sense. We don't need the absolute value. And why does it make sense that we have these non-differentiable points? Well, remember that tangent is not continuous. Tangent has the asymptote. So everywhere that tangent has an asymptote, that's going to be the non-differentiable point of our graph. So there we go. Negative tan of x. Locate the relative extrema. So now we're applying it. Getting straight into it. So how do you find relative extrema? Well, you take the derivative. So 1 over x squared plus 2x times the derivative of the top, 2x plus 2. And we got to set that equal to 0 and undefined, right? So let's say first, where is it undefined? Well, it's undefined at 0 and negative 2, it looks like, right? Okay, good. Yeah, I thought the top might cancel out, but the top's not going to cancel out. So it's undefined at 0 and negative 2. And it's 0 at negative 1, right? When the top is equal to 0, when 2x plus 2 equals 0. So these are our critical points. The negative 1 is kind of the more critical point, but we ought to think about the 0 and negative 2 as well. So when we plug in negative 1, or what? Should we try to use the second derivative test? I'm not against that. I'm not against using the second derivative test. Should we let's do it. That'll be fun. Let's take the derivative again. So the derivative of the top, which is 2, times the bottom, minus the derivative of the bottom, times the top. Interesting. That's how we got the top, though, anyway, isn't it? Divided by the x squared, the bottom squared. Okay. And so now if we plug in and it's positive, we have a positive concavity, it's a minimum. Negative concavity, it's maximum. And then undefined, I guess we still have to think about it. I guess that's the problem. So, yeah, and our undefined is still problematic. But we can plug in the negative 1 here without too much problem. So that's 1 minus 2, it's negative 1, that's negative 2. So that's negative 2. And then, that's 0, right? So it's just negative 2 over whatever you get on the bottom, which is always positive. So this is negative, so that has a negative concavity. So that's a maximum at x equals negative 1. So at x equals 1, or I guess I can say negative 1, and I can even plug in negative 1 to the original equation. What do you get? 1 minus 2, which is negative 1, plus 3, ln of 2. So that should be the maximum. At x equals negative 1, y equals ln of 2. And then, what are these asymptotes? Those are just asymptotes, right? Those are like, we'd have to think about those in terms of increasing and decreasing. But if they're undefined, and they're undefined on the original problem as well, no, they're not actually. So that is going to be a sharp corner. Well, if that's going to be a sharp corner, then we do need to worry about it. So let's actually skip the second derivative test then. We should have done that in the first place. Let's make a sine line. Let's look at the first derivative and let's make a sine line. So let's do 0, -1, and -2. And let's think about if it's increasing, decreasing, or stuff just in between those. So if I plug in a positive number to this derivative, remember, should I rewrite the derivative better? 2x plus 2 over x squared plus 2x. So when I plug in like 1, it's definitely positive, right? There's no way it's not positive here. So when I switch positive, so that means it's increasing. Yeah. And then from -1 to 0, it's decreasing. That's definitely what it would seem here. If I plug in like a -1/2, if I plug in like a -1/2, on the top I get positive. On the bottom, I'd end up with 1/4 minus 1/2. I'd end up with negative. So here, yeah, I am decreasing, which is actually what I thought. But look at what that tells you. That tells you that you do have a minimum here at 0. So this is a maximum, like we already said. We're going to have a minimum at 0, comma ln of 3 when you plug in 0. And then, as we already said, -1 is a maximum. We can confirm that by plugging in like -3/2 and hopefully showing that it's positive. So on the top, you get negative because it's like the 2 would just cancel and it'd be -3 plus 2 and it'd be -1. On the bottom, we're going to have positive 9/4, but yeah, then -3. And that's also going to be negative. So then we're going to have a negative divided by a negative. So that section is a positive. So that's how we know that at -1, it's going to be a maximum. And the last thing we just have to check is a super negative number. So like -5. Well, then the top is definitely negative and the bottom is definitely positive. Right? Because the top is definitely negative. -10 plus 2 is -8. The bottom, -5 squared, is positive 25. And that's like really big. So 25 minus 10 is positive. So negative over positive is negative. So that's decreasing there. So then the question is, can you plug in -2? If you plug in -2, you get 4 minus 4 plus 3. So that's another... That's actually... that's... So I'm getting... So I'm saying that we have a minimum... Oh, I guess no, that makes sense. We have another minimum at -2, comma ln of 3. Is this a continuous graph? It can't be, right? Because it's got to be... Or no, it's not negative because you can't factor it. So this should be a continuous graph. What does this even look like? Is this going to be subtle? Ln of x squared plus 2x plus 3. That doesn't look like it has any maximums. How did I get that? I got that between -1 and 0. And that's actually a min. I thought I got negative concavity. I mean, I was surprised on what it was telling me the graph was looking like. But it feels like that's what I calculated. This was my slope, 2x plus 2 over x squared plus 1, right? 2x plus 2 is the derivative of the top. Oh, it's a plus 3. There's a plus 3 on the bottom. There's a plus 3 on the bottom. Oh my god, I just wrote the problem wrong. Oh. Alright, well that's fine. That's fine. So that just means it's really easy. I'm not going to re-record this because I'm too lazy to do it. But I can almost just start from the top and just run through it really quickly then. Just no problems at all. All right, so this is the first time I've ever seen this problem. What are we going to do? We're going to locate the relative extrema of this equation. So we're going to take the derivative. So 1 over x squared plus 2x plus 3. Don't forget that plus 3 matters. It's not a constant. It's the function. So it's 1 over the entire function. When we take the derivative of it, it'll go away. So over multiplied by 2x plus 2. So that's our derivative. So how do we find local extrema? Well, we set our derivative equal to 0, which would mean that x equals -1, or undefined, which would be when the bottom is equal to 0. But look at how the bottom is never equal to 0, right? We can see that if we want it with the discriminant, b squared minus 4ac is negative. So no solution on the bottom. The bottom is never 0. So the derivative is never undefined, which is awesome. So all we have to worry about then, the only possible extrema, is x equals -1. And then we can just see real quick, is it increasing or decreasing on either side? So if we plug in 0 to this, what do we get? We get positive 2/3, right? So that means on the right, it's increasing. So let's see if it's decreasing on the other side. If I plug in like -5, I'd have like a -8 on the top. I'd have 25 minus 10 plus 3, which would be positive, right? So negative divided by positive. So we're negative and decreasing on that side of -1. So you connect dots. That shows you that -1 is a minimum. And if we go to Desmos and look at the graph, and I just type it in real quick since I've never seen that problem before, there's the graph. And you will indeed see that's where we said, not this. I don't know what that's doing there. I don't know why we called this a maximum. We're just being crazy. We only have that one minimum, and it's right there. That's what ln of 2 is. Ln of, where's the ln? You have to go all the way in here. Unless you're going to type the letters, should just type the letters. Ln of 2 is 0.693, which is what you saw here. Beautiful stuff. Beautiful problem. Beautiful problem. And that's all they got in section 1. So I'll have to see y'all back next time for section 2.